Hello, I'm Dr. Alison Griffiths of Staffordshire University. Contact details are given here, and today I'm going to talk about multi-user CDMA systems and multi-user detection. I'm going to show how we can send an original signal across a shared channel with lots and lots of other users. We're going to spread that signal so it's nice and wide, as shown here. We have other users in this sending information in through this channel. And there will also be some narrowband interference, and I will show how we will recover this signal back again. So, an overview of what I'm going to talk about. What is multi-user detection and CDMA? What are the different types of codes that we can use in code division multiple access? How we spread and despread the message, an example will be given. And then at the receiver, once we receive all our information, how we can recover that information using different types of detectors such as match filter decorrelator, and match filter minimum mean squared error. So, mobile communication systems. How do we get to 3G? There were two major migration paths. Essentially, everyone had the idea of mobile communications at the same time, except the different countries throughout the globe didn't speak to each other. So what happened was we had multiple systems that were completely incompatible. These are the major paths. So in first generation occurred in the 1980s in Europe. There are extended total access communication systems, or ETACs, and there were several versions of these. And in the States it was advanced mobile phone system. These were analog communications, because at that time we used analog, and it was based on frequency division multiple access, in which time each user had a shared amount of space along the frequency channel. So if I use this graph here, if this is frequency, then we would split the channel up into smaller bands, so there would be a lot of wastage because we needed some overlap between, so some space between these bands, otherwise one user would interfere with one another. Hence the number of users, or K, is limited in frequency division multiple access schemes by the number of frequencies. Hence this wasn't a very popular system. Another reason why it wasn't very popular is it wasn't very secure, because essentially somebody could listen in to the particular frequency and they could hear the message being transmitted. So then we moved on to digital communications, which was the second generation, which occurred in the 1990s. This is when all the countries in Europe got together and developed the global system for mobile, or what we know as GSM. It is a TDMA system, so if this is the frequency axis and this is the time axis, what happened was we would split the channel up into, if we had pure TDMA, then every user could access the entire channel for specific periods of time. Then the number of users was limited by the number of channels that we could have, because obviously if we waited too long, then we would experience delays, because we would have to wait too long for our next slot to occur. So what we could do is we could have a mixture of TDMA and FDMA, which is essentially what GSM was based on. So we're split up in different frequencies for different times, and we could hop between different frequencies at different times at some predefined manner. This makes it more secure. Again, in the US, there's also a TDMA counterpart, which is known as IS-54. This was not compatible with GSM, and also at the same time, then in the US, IS-95 was being developed. So IS-95 is the first instance of CDMA. In CDMA, each user is given a separate code which is orthogonal to one another. We will show what orthogonality is. What it means is if I get given a code and I transmit my data using that code, then unless somebody knows that particular code, my data will appear as noise to them. Hence, it's very, very secure. We could also swap codes at a predetermined time. As long as the transmitter and the receiver knows this information, then what was transmitted can be successfully recovered. Again, in the US we had wideband CDMA, and in the UK, in Europe we had wideband CDMA, and the US there's CDMA 2000. CDMA 2000 is backwardly compatible with IS-95, whereas wideband CDMA is backwardly compatible with second generation GSM. I haven't mentioned GPRS, which is General Packet Radio Service, and enhanced data rates for GSM evolution. The reason that they occurred, they are 2.5G, and they appeared because the licensing in Europe was so expensive that GSM needed to be future-proofed, because we couldn't throw, whenever we get to a new generation, we can't throw away the previous generations, because the users will be still using second generation handsets. Nobody uses first generation handsets anymore. So you'll notice in some areas you'll get 3G coverage. Then if you're a bit more in a remote area, you may get Edge or GPRS or just GSM. Hence the backward compatibility and the coverage. So this is where we are. So what about 4G? The reason that we're concentrating on 3G is that 4G is, the idea is still based on it. I'll just go back to 3G as well. The reason we can be backwardly compatible is due to the fact that we now have software-defined radios. So our handset can change its settings, change its connection type to the network based on its location. This is why we can also connect using Wi-Fi using a smartphone. So now 4G. 4G is aimed that we will have a peak speed of 100 megabits for high mobility users and 1 gigabits per second for low mobility users. These have been specified in March 2008 by the International Telecommunications Union Radio Unit, ITU-R, as IMT Advanced. There are two versions. There is long-term evolution, LTE Advanced, and also mobile WiMAX Release 2. So this will be used in the cellular, and this can be used in for the high speed link, which is more like a Wi-Fi and WiMAX. So IP telephony will be used, and orthogonal frequency division multiple access. If we think of code division multiple access that we're going to talk about now, if that is a serial communication, like a serial circuit, then OFDMA is each user's data can be transmitted in parallel. So we can either transmit multiple copies of the data if we don't want to make any errors, or we can transmit, say, bit 1 on channel 1, bit 2 on channel 2, bit 3 on channel 3. So this is how we can get the higher speeds. The other thing that we can have is we can have multiple antennas. So our mobile phone, rather than having a single antenna, can have multiple antennas. 5G, 5 generation, there's no particular specification that describes what 5G will be. There's nothing's been published by a standardization body. However, updated standards that define the capabilities beyond 4G are currently under consideration. These are going to be grouped under ITU-T 4G standards. I'm sure there will some 5G standards will soon emerge. So, what is CDMA? That's the next point. So CDMA is the multiple access technique in which many users share a single channel resource, code or power. The bandwidth in a CDMA system is very much greater than the minimum required bandwidth for the signal transmission. A pseudo noise or PN random signal converts the narrowband signal to a wide band noise-like signal. Now we're going to look at the different types of signals in a future slide. The original signal is multiplied by a very large bandwidth spreading code. So if we've got our narrowband signal, we multiply it by a very wide band code, which gives us a very wide band signal that we transmit. The PN has a much larger chip rate or frequency than the signal data rate. So what we're essentially doing is, if we have 1 bit of message, we're sending that, we're multiplying that by multiple chips for our code. We will go through this in the next few slides. Each user has got its own individual code, which is orthogonal or near orthogonal to all other PN codes. We'll look into this again. The receiver needs to know that code, or essentially it needs to know how it was transmitted, and it needs to be in synchronization with it. And it also, the power of all the users at the receiver determines how much noise there is after signal despreading and demodulation. It is therefore necessary to control the power of each user in order to avoid excessive interference. I'll just do this with a diagram now. So imagine if we have a base station or a node B here, and we have one user here, and we have one user here. Now, in traditional mobile phone systems, all users transmit at the same power. So this signal is travelling this distance, D1. I'm using this notation because this shows a radio signal, and this signal is travelling D2. Obviously, D2 is much less than D1, and the power, due to attenuation of the path, is going to be the received power at node B from the user 2, so P2, is going to be much greater than P1. Now, if we're trying to despread these signals, what's going to happen is the signal from user 1 is going to be drowned out by the signal from user 2. So ideally, the received power at the node B needs to be equal. So P2 needs to equal P1, or received power 1 needs to be equal to received power 2. So in this case, what happens is the node B will give instructions to a particular mobile to increase their power or decrease their power dependent on the received power. So the instruction to user 1 would be increase your power, and the instruction to user 2 would be to decrease your power. Now obviously these users do move because they're mobile nodes, so if user 2 decided to travel away from node B, so the distance is getting larger, node B would be telling that user to increase their transmission power, and consequently if user 1 was moving towards node B, then it would be told to reduce the transmission power. Obviously this is for transmission from U1. Node B would be transmitting downlink packets, because from user 1 to node B is uplink, from node B to user 1 is downlink. It would be transmitting those packets using the required power also. So what does the system model look like? Here we have the message, which is our 1s and -1s. And then we feed this to our transmitter. We then multiply our spreading code. We multiply it if it's in ones and minus ones, whereas if the input data is ones and zeros, then we use the exclusive OR. Exclusive OR and multiplication is the same thing. We use exclusive OR when we're using logic gates, whereas we use ones and minus ones when we're thinking in terms of voltages. We'll need to convert the 1 into, say, a 1 volt and a 0 into a minus 1 volt, or we do it the other way around. So that could either be a 1 could be determined by a minus 1 volt and a 0 is determined by a 1. It just depends. Well, the transmitter and the receiver both need to do it the same way around. So we multiply the message signal by the code, and then this gives us a spreaded signal, the increased bandwidth signal. We then pass that to the channel. If there was other users, then their spreading code, so P2 and say P3, would also be passed to the code to the channel. So this would be P1. So at the receiver, it would consist of our P1 of T, our spread code from message 1, and our spread code from the other users up to PK, and also the noise. So at the receiver, the received signal R of T is comprised of the message times the code plus any other users, P2 to PK, plus the noise. I'm going to assume that there's no other users here at this moment in time. So the D of T is we multiply the received signal by the same code, and then we should recover D of T. And then D of T should be almost equal to M of T, if we've done the operation right, with some errors. And those errors are dependent on the signal to noise ratio of the channel, which is equal to the signal power and the noise power. We will look at this relationship in more detail. So, if our message is comprised of ones and minus ones, as I mentioned before, in the time domain, so we've got 5 bits being transmitted here, then in the frequency domain, we have a square wave, so we have a very narrow band signal. So that's the bandwidth of our signal, our message. This is a bilateral spectrum, so it's essentially from 0 to there. So that's twice the bandwidth of the message. So our spreading code, in this case, we have 8 chips for 1 bit. That is repeated for every single bit here, 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 and here. So if we have a 1, essentially we multiply the 1 by when we have a 1 and we get a 1. When we have a minus 1 on our code, we multiply it by 1 and we get a minus 1. So essentially when we have a 1, we have a copy of the spreading code. When we have a minus 1, we have the inverse. Here we have a copy, here we have a copy, and here we have the inverse. In the frequency domain, we can see that because this is 8 times higher chip rate, then the bandwidth of our signal is much larger. The bandwidth is determined where we get to the first null, and again here that is 2. The bandwidth, twice the bandwidth of the spreading signal, or A. When we multiply the two together, the bandwidth of the resultant is actually slightly wider, but it's still 2BA. And then we will add noise to our signal. Now the noise only appears at those frequencies. So what does this look like? We have a narrowband, or BM, of the message bandwidth of the message signal. So this is the Fourier transform of the message signal, which is the capital M in terms of omega, or frequency. So and A is the signal, the spread sequence. BA is the bandwidth of the spread sequence, and when we multiply the two together, then P of the spread signal is given by P omega, and its bandwidth is greater than BA, so BA plus half of BM. Here we've got the power is message times spread signal, or the exclusive OR of message omega times A omega. So BA is much greater than BM. Then this is convolution, exclusive OR, sorry. BP is approximately equal to BA. This gives us the BP is the bandwidth of P. So that is approximately equal to BA. So we can say that this is sufficiently small that the gain, or the processing gain, is the bandwidth of the spread encode divided by the bandwidth of the message. So what's the ratio between the frequencies of the message signal and the spread encode? And that's the processing gain. So before spreading, we've got a narrowband signal, and then after spreading we have a wideband signal, and we also have the noise. The noise is determined by sigma squared, which is the variance of the noise power times the bandwidth of the message only. This is important, that it's only the bandwidth of the message. But the processing gain is BA over BM, as we've just shown. After spreading, the signal to noise ratio of our A is P divided by G sigma squared. But after despreading, the signal to noise ratio of our message now only occupies this frequency, so 0 to BM. So the signal to noise ratio of our message is equal to P divided by sigma squared, which is why sigma squared has the BM here. So we only get the noise from here to here, not from here to here. If the codes are all orthogonal to each other, the multiple access interference, or the interference supplied by other users, is 0, and therefore theoretically an infinite number of users can use the channel if the power at the receiver is the same. So we have the strict power control, as I already mentioned. So what does this look like? For multiple users, so we've got user 1 here and user 2 here, occupying the same bandwidth, just a different colour. They're shown in this graph as on top of each other because they're additive. However, when we despread the signal, the multiple access interference is just slightly higher because it looks like noise. And again, the noise is only effective at this bandwidth, not the entire bandwidth. So this is how we can have multiple channels travelling through the same channel if they are totally orthogonal, then this multiple access interference would not have any effect whatsoever. It would just be the same as the noise. So if we do this in terms of the equation, then the received signal R of t that we had before is comprised of M of t, A1 of t, M2 of t times A2 of t plus N of t. Now again, we could add more users here. The received signal is still R of t times A1 of t, however R of t has changed. So what we have is we have M1 of t, A1 of t times A1 of t, P2 of t, so the power of our second message, times A1 of t. So essentially P2 of t is A2t, M2t, A2t times A1t, plus noise, or the additive white Gaussian noise, times A of t. So the interference is given by P2 of t times A1 of t. The desired signal is A1 of t times A1 of t, and we will show that if we multiply two spreading codes together, because they're orthogonal, then we will get the identity matrix with a gain of the spreading gain. So essentially we will get gain M1 of t at the output. So if we divide by the gain, then that means we should recover the message. Previously we had a gain of 8. What this means is if one error was received, or one bit was received in error of those 8, then we would still get the correct results. If 2 bits were received in error, then 6 would still be correct, so we'd still get the correct result. If 3 bits were received in error, then 5 bits would be correct still, and we'd still get the correct error. However, if 4 errors were made, then we'd have 4 bits correct in error, 4 bits correct, so we would possibly not get the correct result. If 5 errors were made, we would get the wrong results, and so on and so forth until we get to the processing gain. This is why CDMA is so robust, because a number of errors can be made and we will still get the right result. So we've talked about what CDMA is. Now we're going to talk about the different types of codes. They are grouped into 3 categories: orthogonal, these are the perfect ones, the Hadamard-Walsh, so each code has no effect on the other code; semi-orthogonal, and we'll explain why we need semi-orthogonal, and these are known as gold codes; and then just a totally random code. So if we had a series of ones and minus ones with equiprobability of occurring, so it's a completely random code, so we will show, depending on our detector, then how effective random, semi-orthogonal and orthogonal codes are compared to each other. You will do this in your laboratory exercise using MATLAB. So, first of all, the orthogonal code. This is known as the Hadamard-Walsh code. First of all, we have a 2 by 2 code. So we assign the 2 by 2 matrix. Then if we have 1, 1 on the first row and 1 on the second row, and finally have the inverse of 1, so minus 1 in the bottom right hand position, or column 1, row 1. It's highlighted here. So we could have, the spreading gain would be 2, and the number of users would be 2. So if we then created a 4 by 4 matrix, what we would do is we would copy the contents of the 2 by 2 matrix to the uppermost elements. We would copy them down to the second and third row as shown, and also across the first line, and then in the bottom right hand corner, which is highlighted, we would reverse. So inverse, minus 1 where 1 was, and 1's where minus 1 are. So you'll see that the transpose and the original matrix of these are equal. Hence, when you multiply the two together, you get the identity matrix. You can try it if you like. So, in this case, for the 4 by 4 code, we would be able to have one user having this code, the second user having this code, the third user having that code, and the fourth user having that code. and the gain would be 4, and we could have 4 users. We could do this again for an 8 by 8 matrix, so we copy the entire 4 by 4 matrix up here, and we follow the same procedure, copying it there and copying it in the bottom left hand corner, and then this is the inverse. So this is the 8 by 8 matrix, so we could have a maximum of 8 users. Obviously we don't have to use all of the rows, but the spreading gain would be 8. The problem with this is we've got a fixed spreading gain. So for true orthogonality, for example, we couldn't give this as a spreading gain. If we gave the code here for a spreading gain of 4 for one user, those spreading gains are the same. So this is a subset of this. They're all subsets of each other, so these are not very practical. If we've only got a small number of users, then these are very secure. However, they're not practical. For this case, we use semi-orthogonal codes. So in a semi-orthogonal code, computers cannot generate random numbers, as you probably already know. So what we'll use is D-type flip-flops or a shift register. Here we have 4 stages in our shift register, very similar to how convolutional encoding is done. It's known as a PN generator or a pseudo-noise generator. And what pseudo-noise means is it is pretend noise. So it's pretend random. So it isn't really random, because after a certain period of time, that the output repeats itself. And the output repeats itself after 2 to the power of m minus 1, where m is the number of memory elements. So in this case, 2 to the power of m is 2 to the power of 4, take away 1, which is 15. The reason it's take away 1 is because you will be in a certain position, and then this position will repeat itself. What do I mean by that? Okay, so I shall show you. So imagine the contents of each shift register are as shown here. So we have 0, 0, excuse me a second, 0, 0, 0, 1. The initial conditions, if everything is 0, then this won't work. So we need to have a NAND gate connected to all of these. In reality, a NAND gate to ensure that the 0, 0, 0 condition never occurs. And what happens is we choose certain outputs of the memory elements to feed back to the beginning. So there's no input here. The output is the feedback stages of whatever we choose. In this case, it's the output of 3 and 4. So the output in this case, I've chosen it to be 1. I could choose any configuration here. The result would still be the same. So we'll have these 0, 1, 1, 2 and 3 as 0 and 4 be 1. So here, if we've got a 1 here and a 0 here, then the exclusive OR to that would be a 1. The truth table for exclusive OR, as I've said, is 0, 0, 0, 1, 1, 0, 1, 1. So for that it's 1, and those two it's 0. So 2 zeros is a 0, 1 or a 1 0 is a 1, and a 1 1 is a 0. We can have more than 2 inputs to an exclusive OR. If we remember the term, if there's an odd number of 1s, the output is 1. If there's an even number of 1s, the output is 0. Or 0, of course. So what we then do is we send this output 1 and 0. The output is 1. It gets fed back to position 1. Then everything shifts to the right one. So we have a 1 here, and then these 3 zeros are shifted 1, 2, 3, because this is what a shift register or a D-type flip-flop does. Again, I'm showing 1s and 0s here because these are generated by Boolean algebra. So 1s and 0s. Now we have a 0 here and a 0 here, so the output is going to be 0. So we're going to have 0, and then these are going to be shifted, so we've got 0, 1 here, 0, 0. Hence we have 0, 1, 0, 0. Then we have 2 zeros still on the input, so we have another 0. So the output's going to be, the next line is going to be 0, 0, 1, 0. Then now we have on the output to shift register 3, we have a 1. So the input here is going to be a 1. So we're going to have 1, 0, 0, 1 as the next line. And hence 1, 0, 0, 1. We repeat the process over and over again until we come to a point where we notice that the contents of the shift registers match the contents of the shift registers. This is the point at where the sequence is complete. So this is my entire sequence of pseudo noise sequence. This is the pseudo noise code that's being output from this circuit. One user could be given this code. You'll notice that this code here, or you might notice that this code here, is time shifted by 1. So essentially every single output is a time shifted version of the other. So that's time shifted by 1, that's time shifted by 2. So that's 1 time shift, this is 2 and 3. So we've got 4 separate codes here, each time shifted by 1. If we try and correlate any of those 2 codes, they will show a low value. It won't be 0 because they're not truly orthogonal. They're only semi-orthogonal with one another because they're similar. They're just not in synchronization. So to make this more orthogonal, we can increase the number of stages, first of all. So in this case, we've got 4 stage, which is the same, a 6 stage and an 8 stage. So the length of the 6th stage, so the time before the code repeats itself, is 2 to the power of m, take away 1, 2 to the power of 6, take away 1, so it's much greater, and 2 to the power of 8 minus 1 for the third one. We can see that the outputs are the last one and the previous, on the penultimate one, take away 1. For the 8 stages, we have 4 feedback stages. Now, you have to look in literature because to get this optimal length code, it's not you can't just pick a random number of feedback stages. Only certain stages work. I mentioned gold code in the title, but we've not actually mentioned gold code yet because we're just talking about PN. So for the pseudo noise, as I mentioned before, the trouble with the orthogonal is we had a fixed gain. With the pseudo noise, we can choose the number of chips to represent the code, and it won't affect the semi-orthogonality. However, to make it orthogonal, in a gold code generator, what we do is we have 2 shift registers working in parallel, and then we exclusively OR the outputs of those 2 to provide the final output. So in this case, we've got a 1, 2, 3, 4. We've got 5 stages. So this repeats after 2 to the 5 minus 1. And another one, which also repeats after 2 to the 5 minus 1. But they're completely different. So when we combine the 2, we exclusively OR this one with this one. And we get the output. So this is how gold code sequences work. Don't really need to explain random because this is just totally random. I've already described it. Okay, so when we generate the code in MATLAB, what I've done here is got 3 examples. S, we choose S depending on which type of code we want. If you're simulating orthogonal, then we comment out these and this one. And vice versa, so you need to comment out each one. So we have the Hadamard function in MATLAB. So we just say what size we want the matrix, and then we are scaling down the output because it won't give us 1s and 0s. It'll give us what the square root of n. What I meant to say is it doesn't give ones and minus ones, it gives the amplitude of square root of n. Then if we want to generate the gold code, then we would comment out these two lines and uncomment these by taking the percentage signs away. S1 and S2 are the generator matrices for the pseudo noise shift registers. So the first input will be connected in the exclusive OR, and the third one, and then the first three and the last one are connected in the exclusive OR. You will be explained this in your laboratory sessions. Again, the output is scaled down by 1 over the square root of the size of the number of codes n, and the HG is the cyclo function, which you can download from Blackboard, and we have the two S1s and S2s. The actual n in this case is defined by the number of taps that we have here on the pseudo noise generator. So we have 1, 2, 3, 4, 5 in this case. Then the random code is just ones and minus ones, and we again sign them. We again scale them down, and we have K users, so we use the first one to K. So the output signal to noise ratio, if our input signal power is P for all users, the noise power is given by the variance, or sigma squared, which is the noise floor times the bandwidth of only the message, not the bandwidth of the spread code, so the narrow bandwidth. Then the effective interference power is given by P divided by the gain, or the spreading gain, which is also equal to the chip rate. The chip rate is essentially how much faster how many bits per chip that we have, so how many bits in the spreading code we have compared to one data bit. The total noise power is therefore the variance, or the sigma squared, plus P over G. So the interference power, or the multiple access interference, this is the power that is by other users transmitting on this network at the same frequencies. So then this is the MAI, or multiple access interference. So the signal to noise ratio at the output is given by P, the signal power, divided by the total noise. So this is the addition of the noise and the multiple access interference. So P over sigma squared plus P over G. So if we divide every single term by sigma squared, that gives me P squared, P over sigma squared over sigma squared, which cancels to 1, plus P over G sigma squared. P over sigma squared is the signal to noise ratio of the message. So we can further reduce this equation down to SNR of M divided by 1 plus SNR of M over spreading code, or G. We need to remember this for later use. So as I've already mentioned, at the receiver side we have our actual message times our spreading code, so message 1 times spreading code 1, plus message 2 times spreading code 2, all the way up message 3 times spreading code 3, all the way up to message K times code K, plus our noise. And we always have the receiver, so this would be D1 D1 of t is RA1. So D, for instance, D2, so at user 2, D2 of t would be R times code 2. And DK would be R times AK. So code K times T. But for our user 1, the received signal D1 is M1 time, or approximately M1 times A1 times the other A1, because R is this, excuse me a second, is this times A1, every single term here, so it's also P2 times A1, so this would be P2 is the power of this, and PK A1, because we've only got A1 at the receiver, so we're not despreading message 2 because we don't have code 2. So what we receive is P2, so this is the wide spreaded multiple access interference from user 2. Here, PK, this is the widespread signal from user K. And then also the noise times the spreading code 1, and that is just the same as saying the noise. Because when we've shown that when we multiply a spreading code with nothing but noise, then we still get noise. So the signal is these two get rid of each other, plus we have some spreading gain. Then we have the second power P2 times A1 plus PK times A1, and we've shown previously in the previous slides that these are wideband interference plus the noise. So our signal has it's much narrower now, and it has a high amplitude. So again, we always want to find the signal to noise ratio at the output so that we can predict the bit error rate. The bit error rate is we count how many errors made. So when the transmitted symbol doesn't match the received symbol, then an error is made. We divide that by the number of bits transmitted. And this is the bit error rate. Here we have the same thing shown pictorially. So we've got user 1, 2 and K all occupying the same narrow band bandwidth from 0 to BM. These are all in the frequency domain, or omega. Then we spread the signals, and they're shown on top of each other here, just so that we can see them all. And we also have the noise here, or sigma squared, which is N0B A, and then we despread our actual signal with code 1, and then we have the approximate, so we've got the approximation sign here, message signal from message 1 plus the noise here, and then we've got the interference from user 2 to user K. And obviously this goes on to a much higher bandwidth, which is twice BA, but we can use filters to only take into account the signal that we're interested in. So, high signal to noise ratio of the message. Here we have the original equation that we have defined in terms of signal to noise ratio of the message in the spreading game. So if we have the same equation, then the multiple axis interference now is given by the number of users that we have, which is k, take away 1. The reason it's take away 1 is because we're one of the users and we can't interfere with ourselves. So k minus 1 times p over g plus sigma squared, all divided by p, is the signal to noise ratio at the output. So if we then put that into the equation, then we're saying we've got a very high signal to noise ratio of our message. So if we're tending to infinity here, then infinity divided by infinity are going to cancel. So we will have g infinity over 1 is going to be infinity, plus k minus 1 over g. Invert this, g over k minus 1. K is approximately equal to k minus 1. So k equals g over signal to noise ratio at the output. So what we're trying to say is in CDMA there is no reuse factor, or the reuse factor is 1. If the codes are orthogonal or semi-orthogonal, then we can use the codes, or there is no reuse factor. The only thing that limits us is the multiple access interference and the fact that the difference in power levels, because if P is not the same for all users, as I've shown before with the near far pod problem, then the multiple access interference will be affected and obviously there will be a degraded performance. Compare this to the reuse factor for frequency and time division multiple access when we've got 1 in 7. We've got 1 in 7 here because we have a cell size or a cluster of 7 cells. Then the channels that are used in cell A are, if we have 100 channels, I should have used a better number, but we've got 7 channels. So in here we have 100 over 7 channels can be used in each cell. We don't want to overlap these cells, so the channels, say the first channel will be used in channel A, the second channel in B, third C, fourth D, fifth E, sixth F, seventh G, eighth back in channel 1, the ninth in B, so on and so forth, because we don't want the channels to be next to each other because then they're going to interfere with each other more. So the distance between where a channel is used and it's used once and whether it's used in a different place is this distance from the centre of cell A to another cell A, and those distances should be equal. We will go through this in a tutorial. So, multi-user channel capacity. If we have n multi-users, basically what we're saying is because it's CDMA, the capacity is equal to the sum of all the powers and all the receivers, receiver 1, receiver 2, receiver 3, up to receiver M. And what we're saying is because the channel reuse ratio is 1, then we have every user can use the whole channel. So the channel capacity is at a maximum, so it's not limited by the number of users. This has no effect. So we just have C, channel capacity is log to the base 2, 1 plus P over N. Okay, an example of how we spread and despread messages. If we go back to our system model, we have the message M of t. Then we spread the message at the transmitter, A of t. We have P of t coming out. Then the channel, we add noise to P of t and also possibly other users. Then at the receiver, we receive a signal and we multiply that signal by A of t. So R of t equals message of t times A of t plus N of t. D of t is the received signal times A of t. If Y is our received signal, then we have the signature matrix X plus N. We'll just define the fact that N is the spreading gain in this case. So, and K is the number of users. So if we have a transmitted symbol, we have the first bit and we have K symbols being transmitted at the same time because there are K users. We multiply that by the signature matrix, which is of size N times K. So if we have a multi-user system model, we have Y, or the received signal, equals S, which is the signature matrix. That would either be the orthogonal or semi-orthogonal or random code. And we have X users and we're adding noise. Y, basically we have X bits transmitted at the same time and each uses a separate code. Y is an n by 1 matrix. X is a k by 1 matrix or a dimensional vector. And S is the signature matrix, which is n by k. N is the spreading gain and k is the number of users. So if our original signal is user 1 is transmitting a 1, minus 1, 1, 1, 1, then that signal, so this bit here, would be spread n times. So we would say 1, minus 1, 1, 1, 1, minus 1. I'm making up these codes now. 1, 2, 3, 4, 5, 6, 7, 8. So that would represent what was transmitted for user 1. User 2, we would multiply minus 1 by the second code. 1, 2, 3, 4, 5, 6, 7, 8. And then I'll do the same for the other users. 1, 2, 3, 4, 5, 6, 7, 8. Up to the bottom one. So this is our X. Our S times X is a square matrix. Times X is a square matrix. Then we might not use, if this is 1, 2, 3, 1, 2, 3, 4, 5, I used only five users here, but we've got 1, 2, 3, 4, 5, 6, 7, 8. So in our case, the spreading gain is 8 and the number of users is 5. So S times X is So when we have a very large number of users, we've said there's not really a limit, but the capacity is reduced when we have a high interference. This is caused when the codes are not quite orthogonal or semi-orthogonal. I've explained why we can't always use orthogonal. The capacity is reduced by this L of Y. So when interference is very low, Y equals 0. So Ly is 0. So the capacity isn't affected because nothing is taken off. When interference is large, then we have infinity or heavy interference, then capacity is reduced by that amount. The symbol loading, or Y equals K divided by N, is a measure of the interference, so the number of users over the gain, and L of Y is the loss due to the presence of interference. So looking at the CDMA system model, we've talked about this a lot, but now we're going to see it in pictorial form. Here we have user X1, then it is transmitting a symbol, a 1, say, for instance. Its S1 is its code or signature matrix 1 that will be multiplied if it is 1s and minus 1s, or exclusively ORed if we're talking about 1s and 0s. The reason that we talk in 1s and 0s is because when we're implementing in hardware, we might be using logic. However, if when we're transmitting across the channel, we'll be transmitting different voltage levels, so we can't transmit 0 volts, so we use bipolar, so we use a 1 volt and a minus 1 volt. Sometimes 1 volt is represented by a 1 and minus 1 a 0. Sometimes we can have reverse, and 1 can represent a bit 0 bit, and minus 1 represents a 1 bit. As long as the transmitter and the receiver are both aware of what voltage level represents a 0 bit and what voltage level represents a 1 bit, then the signal should be received correctly. So here we multiply our signals, so rather than having just a 1, we have, let's say the spreading gain is 5, for instance, we would have 1, minus 1, 1, minus 1, 1, 1, 2, 3, 4, 5. So we'd be transmitting 5 bits rather than the single bit that we had. Then at the receiver, then we pass this to the channel. This is S, and we would add some noise. Then at the receiver, we would multiply our received signal, or Y, by the same S1, so by our 1 minus 1 before S1, and then we should recover X hat 1, or X hat should be equal to X1 if there is no noise and if the codes are orthogonal. Transmitter 2, we have X2, then transmitter 2 will be transmitting their value, and they will have a separate code, unique to S1, not unique. So then what we're passing to the channel is S1 times X1 and S2 times X2. We're adding them together, and then we're adding the noise. So Y is now composed of users 1 and user 2 data plus noise. And then at the receiver, if we multiply the code by the multiply Y by the respective code, then we should be able to recover X3. Now if we have a different code and that wasn't transmitting any message, then we should recover random noise until we have K users, or the kth user, and it has its own unique code. then we show this as y equals sx plus n. So we represent this as a one-dimensional matrix and S is a two-dimensional matrix. So if this is rows and columns, then this would be X, this would be S, and then we're adding noise to every single row and element in this matrix. I've drawn them as lines, these should be separate elements, and then at the output we multiply the received signal with the respective code and we should get an estimation of what was transmitted. I'm going to go through an example in a minute. So here, in this case, if a 0 bit is represented by 1 volt and 1 bit is therefore represented by -1, then if we consider 3 users and 4 orthogonal spreading codes, you'll notice here that I've reproduced the Hadamard matrix for a 4x4 column matrix. So I've picked the first row to represent the spreading code for user 1, the second row to represent the spreading code for user 2, and the third code, or row 2, to represent the spreading code 3, and then we have a spare spreading code because we only have 3 users in this case. So if my input data is 0, 0, we've said here that a 0 bit is represented by 1 volt. So here I've put the 0 bit is 1 volt, the second bit of user data is 0, and again that is represented by 1 volt. Here's our spread code. Similarly, if user data 2 is 1, 0, then a 1 is going to be represented by a -1 here, and a 0 again with a 1, and then this is user 2's spread code. User 3 is going to be transmitting 1 and 1, and their representation is a -1 volt and -1 volt, and their spread code is given here. So because we're using 1s and -1s, we can just simply do a modulo 2 multiplication. If we kept it in terms of 0s and 1s, then we would just do an exclusive OR operation. And I've showed why we use 1s and 0s, because the shift registers use 1s and 0s. So, data from user 1. We're transmitting 1. So we have this first data bit, and then we're going to multiply it by the 4 bits. In our case, in this case, our G equals 4 and our K equals 3. So we've got K users and a spreading gain is 4. So for the first bit, we transmit 1, 1, 1, 1, because it's 1 times 1, 1 times 1, 1 times 1, and 1 times 1. For the second bit, then we repeat the same code that we already had, the 1, 1, 1, 1, with the second bit of data. So again, we transmit 1, 1, 1, 1. We do the same thing for the second user. So here we're transmitting a -1, and we copy the code down, 1, -1, 1, -1, to code 2 here, and then we multiply out -1 times 1, which is -1. -1 times -1 is +1. -1 times 1 is -1. -1 times -1 is 1. So that's the first bit encoded or spreaded. Then the second bit is a 1, and we copy this code 1, -1, 1, -1 again. So 1 times 1 is 1, 1 minus 1 is -1, 1, 1 is 1, 1 minus 1 is -1. So this is the spreaded message 2. In a spread the message 3, and we would get the following code as shown here. Okay, so this is our S1, x1, x plus x2, x2 plus x3, s3, or s3, x3. So now what we need to do is add them together or combine them to make the composite. So if I draw this in terms of voltage waveforms, so I've used this representation here. 1 is here, 0, it's at the bottom of the cell, -1 is represented by the bottom line. So user spread data is all the ones. User 2 spread data is this waveform as shown here. So -1, 1, -1, 1, 1, -1, 1, -1. User 3 data is -1, -1, -1, plus 1, plus 1, -1, -1, plus 1, plus 1. So the composite waveform is the addition of these three at the different instances in time. So it will be the addition of these 3 bits, then the addition of these 3 bits, and the addition of the following 3 bits. So we have 1 minus 1, which is 0, minus 1, which gives us -1. That's for the first bit. The second bit is 1 plus 1, which is 2, minus 1, which gives us 1. Then we've got 1 minus 1 plus 1, which gives us 1. Then we have 1 plus 1 plus 1, which gives us 3. 1 plus 1 is 2, minus 1 is 1. 1 minus 1 is 0, minus 1 is -1. And 1 plus 1 is 2, plus 1 is 3. 1 minus 1, 0, plus 1 is 1. So the composite waveform is shown here. And I've written it as -1, 1, 1, 3, 1, -1, 3, and 1. Okay, so I've copied what was transmitted here. And then composite waveform is our Y from our previous example. In this case, we've assumed noise equal to 0, or a signal to noise ratio. If noise is equal to 0, signal power of a 0 divided by a 0 noise power, so it's an infinite signal to noise ratio. SNR tends to infinity when noise equals 0, because it's signal power over noise power. Okay, so if we are in receipt of Y and we have, say, spread code 1, so we're in possession with this spread code and we know it's in synchronization with what was transmitted. So what we do is we multiply our spread code with the composite waveform. So we have -1 times 1 is -1. 1 times 1 is obviously 1. Because we're multiplying everything by 1, we essentially have our spreaded code, or composite motion times spread code is equal to the composite waveform. So -1, 1, 1, 3, 1, -1, 3, and 1. Now, if we sum the resultant up, so that we get -1 plus 1 plus 1 plus 3, we get 4. Then we divide it by the chip rate, or the spread code, which is, or the gain. This is also equal to the gain. So 4 over 4 gives us 1. And we said a 1 represented 0. So 1 represents a 0 here. And hence a 0 was actually transmitted. Same thing again for the second bit. 1 minus 1. 1 minus 1 is 0. Plus 3 is 3. Plus 1 is 4. 4 over 4 is a 1. 1 equates to a 0. And 0 was in fact transmitted. So we've recovered the user 1 data successfully. Well done. So if we're in possession of spreading code 2 and we receive the composite waveform Y, then we obviously do the same procedure again. So 1 times -1 is -1. minus 1 times 1 is minus 1. 1 times 1 is 1. Minus 1 times 3 is minus 3. 1 times 1 is 1. Minus 1 times minus 1 is plus 1. 1 times 3 is 3. And minus 1 times 1 is minus 1. So then we have minus 1, which is minus 2, plus 1, which is minus 1, minus 3 gives us minus 4. Minus 4 over the spreading gain, 4 is minus 1. Minus 1 represents a bit 1, so the transmitted data is 1, and it was in fact 1. We do the same thing with the second bit. 1 plus 1 plus 3 is 5, take away 1 is 4, 4 over 4 is 1, and 0 was transmitted. So we'll spread code 3, and I'll leave you to do that, but I hope you will confirm that 1 and 1 was transmitted. Now the final question is we didn't actually transmit any using the spare spreading code. Now, what happens if I multiply this spare spreading code by the composite waveform? Actually, what we get is zeros out. So minus 1, minus 1, minus 1 is minus 3, and then we get plus 3 there is 0. So in each case we get zeros out, so nothing was transmitted. The reason we get 0 here is because we used the Hadamard or the orthogonal codes, and also no data was added. No noise was added. If there was some noise, or if they were semi-orthogonal or random, then we would get some small random noise appearing here. However, we would still not be able to determine whether a 0 or a 1 was transmitted, and that doesn't actually matter. But basically what I'm saying is if you're not in possession of a valid code, then you're not able to decode what was transmitted. That's the main point of what I'm saying. Okay, as I've already mentioned, it will already work for opposite voltages as long as the transmitter and the receiver have the same voltages. And also if we used exclusive OR, if we didn't convert to voltages, we just use ones and zeros, we could use the exclusive OR to do the spreading operation. XOR is easier to implement in hardware using logic gates. However, when we're transmitting BPSK or QPSK, then we need voltage levels. So the final section, we've talked about message spreading and despreading, is the actual detection. So once we receive our signal, in reality, we need to have, there are 3 different types of detectors. They're all known as the matched filter family, being from the simplest to the more complex, and they're then more complicated. It depends on the application as to what accuracy required and what the channel conditions are. So the simplest case is the matched filter, then the matched filter decorrelator, and finally the matched filter minimum mean squared error. We will talk about what each of those are. Again, you will do this in your laboratory session. So this is the history of multi-user detection. So in 1986, so not that long ago, S. Verdue defined that the capacity C is achievable with a receiver that has exponential complexity. In 1990, the capacity is nearly achievable with linear complexity. So we want to have a less complex receiver, so when we want to achieve the channel capacity. In 1994 and 5, the adaptive minimum mean squared error, CDMA receivers, were defined. They're linear complexity receivers, and they are adaptable to realistic cellular mobile environment, such as fading environment, narrowband interference, multiple access interference, and also unknown signatures. So you'd be able to find these research papers. They may be useful for your assignment. So the classification, we have matched filters, we have maximum likelihood, because obviously when we're receiving a sequence, we don't know what was transmitted, so we go by what was most likely transmitted. What's the bit error rate? We've got maximum likelihood zero forcing, minimum mean squared error, and we're going to explain what the decorrelator is, the zero forcing, and the minimum mean squared error, which is given by R plus sigma squared identity matrix to the -1. Then we've got zero forcing, minimum mean squared error, differential feedback equalizer, and the MFML. We're just going to look at the top three. There are more complex receivers, which are known as adaptive receivers, so they change according to the channel conditions. However, that is a more complex course and could be studied at master's level. So, the three multi-user classifications that we have. First of all, we'll look at the simplest, which is the matched filter. So, in the matched filter, what we have is we have a bank of matched filters at the receiver side, and we detect which, was it a 1 or was it a 0, or was it a 1 or was it a 0, a -1 that was transmitted. So 1 or a 0 here. So a single match filter, single user, so our Y consists of signature matrix, or our code 1 times our bit 1 plus our noise. We're saying that our expected value of our noise is sigma squared. So the output at the match filter is we won't worry about this Hermitian, it's a mathematical term, but what we're saying is we can do this in MATLAB. We multiply the signature 1 Hermitian by Y, and signature 1 Hermitian times signature 1 times X gives us our approximate value of X. R1 is, as we've said, signature 1 Hermitian times signature 1 is equal to 1. This is a mathematical function, since the magnitude of our spreading code squared equals 1. Okay, and it's the normalized power. So R1 should equal 1. So here, X1 at the match filter should equal the original X1 plus our noise. So at the output, we have X1 plus some noise, and that's the decision of the match filter. So as long as the signal to noise ratio is low enough, the noise power is low enough, or signal to noise ratio is high enough, then we're going to get the correct decision. However, if the noise is high and the signal to noise ratio is low, then the match filter could give the wrong decision. So then we use a little bit more mathematics to try and make a better decision, or to improve the bit error rate. So, in this case we're using two matched filters. So the output is Y is signature 1 user 1 plus signature 2 user 2 plus N. So now we have the same code 1 basically times our Y. So we've got signature 1H times S1, which is essentially 1. Signature 1H times signature 2 times X, which is what we showed before in previous slides. This is the multiple access interference. And signature 1H, our code, times our noise, which is essentially our received noise. And our received noise is the same as sigma squared. So we have X1 now. There is the output or the match filter response from output X1 hat is X1 plus the multiple access interference from the second user and any subsequent users, so that could be K users, plus the noise. Similarly, at X2 match filter, at the second match filter, we have the output of X2 plus the multiple access interference 2, which is essentially the multiple access interference from user 1 in this case, plus noise 2. So now C, the capacity is log 2 of 1 plus the power divided by the multiple access interference. So now we extend it to have multiple users. So the users go from K equals 1 to large K. So the output is the summation of user 1 to K times their own code. So SK, XK plus N. So the match filter output is S Hermitian Y or S Hermitian SX plus S Hermitian N equals received times X plus N. So received is S1H1 times S1, S1H2 times S2, all the way from S1H to S1SK. And then on the downward slope, this is always at, oops, excuse me a second. This is always S1. And then we have S1 Hermitian, S2 Hermitian, SK Hermitian. So these rows are the output for user 1 to user K. So that would be X1 match filter to XK match filter. Now this matrix, we've shown that S1H, well, I've told you that S1H times S1 is 1 and S2H times S2, because we're multiplying by the same signature, that's also 1. And SKH times SK, that will also be 1. So all on this diagonal we have 1s. Now if we have a truly orthogonal matrix, codes for each user, then this would be the identity matrix. If we have semi-orthogonal codes, then, this would just be 1s for the identity matrix, and the alphas would all be 0. However, if we're using semi-orthogonal codes or gold codes, then alpha is a very, very small number. So X hat match filter is approximately equal to X plus 1. If these alphas are higher, then we get a poorer output, but we can also improve on that. So the MATLAB implementation of the match filter, again you will go through this in the lab, is the X match filter is the sign of the signature matrix times Y, the received vector or matrix, and I have then demodulated it. So we're just saying sign. So if it's positive, make it positive. If it's negative, it's negative. So I've already done the multiplication. And then what I've done is X is our input data, and our X demo matched filter, so demodulated matched filter, is 0.5, in this case we have 1s and minus 1s. So if our match filter was a 1, if we add 0.5 to it, it's 1.5. So if we times it by 0.5, it's a half, and we add 0.5, it's a 1. Then if the output was a minus 1, 1 times a half is a half, plus 0.5 gives a 1. If the output was a minus 1, it would be a minus 1 times a half, which is minus a half, plus 0.5, it will be a 0. So basically we're converting to 1s and 0s. The reason that I'm doing that is because to compare how many errors there are, if we exclusively OR the demodulated match filter output with the input data X, then if the two are different, then we'll get a 1. If they're the same, we'll get a 0. So the sum of the exclusive OR of those two matrices will give the number of errors. So I've stored that under error, and then I've added that error to the final error, because this is part of a loop, depending on how many times we're going around that loop. So that's the MATLAB implementation of the matched filter. So what's a match filter decorrelator? Now, in a decorrelator, what's correlation? Correlation is how similar two signals are to each other. So in our receiver, for example, if we're using BPSK, then we have two known symbols that will be transmitted. If we're using QPSK, we will know that there are 4 known symbols that are transmitted, and 8PSK, there are 8, obviously. So what we will do is at the receiver, we will look and see which our received signal is closest to. So we will perform the correlation, perform a correlation on what we've received with each of the 4 symbols, if it's QPSK, for instance, and then we will say wherever the correlation is highest, then that is the one that was sent. So the definition, correlation is the correlation of a known signal or a template with an unknown signal to detect the presence of the template in the unknown signal. It's equivalent to convolving the unknown signal with a conjugated time-reversed version of the template. An optimal linear filter for maximising the signal to noise ratio in the presence of additive white Gaussian noise. So where are decorrelator detectors used? They're commonly used in radar because we send a known signal out, and then a signal is reflected and returns to the transmitter or to the same place, and we examine the differences and how common it is to the outgoing signal. So has the frequency changed? How's the amplitude changed? Are we looking for Doppler frequencies? Pulse compression is an example of matched filtering. It is also called because the impulse response is matched to the input pulse signals. Okay, so this is the block diagram of the matched filter, most likely multi-user detector. So what we have is we have the same block diagram. However, here at the back we have a centralized maximum likelihood detector, and then it will output what it thought bit 1 was from user 1, from user 2 and from user K. Obviously this needs to be done at a base station because that's where multiple users are being transmitted to a common place. However, if you would like to look at it in further detail, you can use OFDM, where we transmit these bits are not necessarily different users. we could be using different channels from the same user. We can then go into the realm of transmit and receive diversity. Again, that's a bit high level for this level, of course. This would be done in the MSc level. So, maximum likelihood detection over a finite set. So, in our example, let's take Q, P, S, K. Need to get a better. S, K. So we have 4 symbols. 0, 0, 0, 1, 1, 0, 1, 1. So, we have our input X, we have our matched filter, no noise, and then we have our received signal times X, and we add noise. R is known, X set is known, and X set, no noise, is also known. So we look at the minimum difference between what we receive and what X would be without any noise. So the capacity of a system with a large number of users is shown in this diagram here. So it's showing the minus Ly dependent on the amount of interference. So in a conventional single cell matched filter receiver, then as the signal to noise ratio is increasing, then the normalized channel capacity is reduced, as shown by this green line. B is the random signature, or statistically orthogonal multi-user capacity, which is closer to 1. And C is orthogonal multi-user system. So we have ideal conditions, and the channel capacity, the whole of the channel, is being used, because obviously it doesn't matter about the interference, because we have total orthogonality. So this is the block diagram of the correlator detector. So at the difference here is we've got a centralized decorrelator detector, and it calculates R to the minus 1. So Y is SX plus N. X match filter, as we've already said, is S Hermitian Y, S Hermitian times S times X plus S Hermitian N equals Rx plus N hat. So if we multiply Rx by R to the minus 1, so we've got R inverse X hat. So R to the minus 1 received match filter X hat equals the X decorrelator. So R to the minus 1 times R X plus R to the minus 1 times R gives us X plus 0 multiple axis interference plus noise. But R to the minus 1 could be very large. How we will implement this in MATLAB, R is defined as S transpose times S. R decorrelator is the inverse of R here, and X decision is the sine of R decision times S inverse times our Y. Y is the original signal, which has then been, in this case, converted to BPSK, and noise has been added. This is higher up in the program, but I'm not showing the whole program here. What we have now is we have X decorrelator. We're in the same way converting it from 1s and minus 1s to 1s and 0s. So we've got X demodulated decorrelator, and we're summing that with the original X, and we're counting the number of errors. Then we're adding that to the final error, and we're we're doing that for a different number of bits, and then we will loop around again in the program for different signal to noise ratios. So that's the matched filter decorrelator. So let's talk about the minimum mean squared error matched filter. So the centralized minimum mean squared error detector is defined by the R plus sigma squared times the identity matrix inverse, or to the -1. Again, this is a centralized MMSE detector. This is the simplest one. So we have again our matched filter, X hat matched filter times Rx plus N. X tilde here is G, which is the spreading gain, times the matched filter. The error, or E, E is what our X tilde is, take away our actual X. And the error is X minus G X hat matched filter. So what we want to do is we want to minimize this error because it's minimum mean squared error. So we need to find the linear operation G over X match filter that minimizes the error. So what's the value of G? So G, minimum mean squared error, now I'm not going to worry about how this is defined, is given by R plus the sigma squared identity matrix inverse. This is a complex formula. It's called the Sherman-Morrison-Woodbury formula, and the multiply out of this formula here, working backwards. The X tilde is G, minimum mean squared error, XMF is this. So X is our X tilde, this is our output. G is this. So G X hat, X plus multiple axis interference, or the multiple axis interference is given by the minus of the noise variance times R to the -1 identity matrix plus sigma squared R to the -1 all to the -1 X hat. And similarly, the noise is R plus sigma squared I to the -1 N hat. So the minimum mean squared error is similar to the decorrelator matrix with sigma squared when sigma squared tends to 0. So when we have no noise, the outputs are the same. Don't worry about the derivation. In MATLAB, the implementation is R minimum mean squared error is equals the inverse of R plus sigma over 2 times the identity matrix, so I of k users. This will be explained in your lab session. And then the sign of the resultant, R MMSE, times our signature matrix times Y. That's our output. That would be 1s and -1s. Again, this is converted to 1s and 0s. And we do the exclusive OR again and count out the number of errors. So quite simply, I know it's not simple to derive, but we're not expecting you to derive it. This is the minimum mean squared error matched filter. This is obviously more complex than the other two, and in your laboratory sessions and your coursework assignment, you will investigate, is that complexity required and under what conditions? So on a visual comparison of the three that we've talked about, if the red component is our signal, the blue is our multiple axis interference, and our additive white gassing noise is represented by yellow, then here we have signal slightly higher power than multiple access interference in this case, and low power additive white Gaussian noise. So in the match filter case, then the signal is exactly the same representation as our input. So the same ratio between signal MAI and AWGN. In the decorrelator, then the MAI is reduced to almost 0, and the additive white Gaussian noise is increased a little. However, for the matched filter MMSE, then both the we have a reduction in the MAI, but not quite as much as the decorrelation, and there is an increase in the additive white Gaussian noise. So this is the best. It gives the best performance overall, but it's more complex. So, match filter based receivers. The parameters that we know in the system receiver, and there are some parameters that have to be estimated. We know signatures on the transmitter spreading sequences. We know the number of users. We know it's an additive white Gaussian noise channel. We know that the spectral characteristics of additive Gaussian noise, and we have said that there is no narrowband interference. For all users, signal amplitudes, timing and carrier we must have timing and carrier synchronization. And for all users, we have the absence of multipath fading, or known multipath fading profiles are assumed. Now, again, if you did the masters, we would look into this case with multipath fading. So in summary, we've answered what is multi-user detection and what is CDMA, what are the different types of codes used in CDMA, what is message despreading and despreading, and we've given an example, and then once we've spread, how do we detect what was actually transmitted? And I've given 3 examples of detectors, match filter decorrelators, and minimum mean squared error match filters. Thank you.